Zahana Roy, presenting to you research work on distributed query processing and data sharing in collaboration with Dr. Aspen Olmsted of College of Charleston. The abstract of this paper is as follows. We have introduction, then we will go to the related work concerning to our work, then we will talk a bit about our motivating example. We will pose our hypothesis, then we will show take up a use case and show a type of query execution against it. It will be an example for us, like implementation of our work according to the example. Then we will go on to the performance overview, and lastly we will conclude our work and talk a bit about the future work. Okay, so data is one of the vital entity in database, and it can be managed by two major database approaches, such as which is known as centralized database management approach and distributed database management approach. Centralized database management approach is a traditional one where all of the data in database is cited on a central location, like it's a centralized database where you get all of the relations in question in just one point, whereas on the other hand we have distributed database approach where the data is uh, distributed over several sites. We have different machines on the network. These machines can be treated as nodes or sites. So in data in distributed database, we can also say that there are autonomous processors that may participate in database operations. One thing to notice is that relational algebraic operations like projection, selection, or joining of queries are relatively much easier in centralized databases than distributed databases, because we have the overhead of transmitting one relation from one site to another. So in that case, computing joins or query executions is a bit conflicting, as there are transmission costs coming into question when we need to ship one relation from one side to another. This is one of the very basic issue of distributed database system. But another thing is that in such a distributed mechanism we can keep backup of data, which is many a times very important to an organization. We can keep a backup to on a different site. If a database crash occurs on site 1, we can pick up the data from site 2. This is called data replication. So one important reason to distribute data is that the organization is itself distributed. We will come to this. We will show how distribution of data can be picturized. Then we come to data privacy and data sharing. So imagine if there are different machines on a network, and we need to share or electronically share, whatever we need to share data from one site to another. And also there should be minimum revealing of data. Like there can be many organizations who do not want to reveal some attributes to everyone. So here comes access control mechanisms. There are three kinds of access control mechanisms, like discretionary access control, mandatory access control, role based access control. We also have row level access control. So when data privacy is another concern to data sharing in a distributed database approach, then there is a trade-off between transmission cost or data privacy. So we will come to this one by one. Let's come to query processing and optimization techniques. This we will take up a semi-join operator to describe this in a distributed database approach. We will also discuss between joins and semi-joins. What is a semi-join? What is a full reducer? As I said, that transmission cost, sending one relation, shipping one relation from one side to another, is a major issue in distributed database approach. And how can data privacy and transmission cost be pose a major the trade-off between uh, in database distributed database approach. So what is meant by distribution of data? Suppose we have a Bank of America headquarters or the central office, and it has many branches, one, two, three, to n number of branches. And suppose I am a customer of branch one, but it can happen that a database crash occurred in branch one. Then it is assumed that my personal records are also kept as a backup in the central office. So the branch one can request data, my data from the headquarters, and in this way, with the help of data replication, we can exploit the benefits of distribution of data. So similarly, we have a digital library, say Charleston Public Library, and we have this is the main branch, and the sub branches are suppose North Charleston, James Island, Mount Pleasant. So this is a distributed framework. Like if I am a member of James Island branch, and I am querying whether a particular journal is present in James Island branch, and if it is not present, it lets me know that it's not present in James Island, but we can bring the journal from the main branch. So the request goes from James Island to the Charleston Public Library, and for a request of the journal requested by Ahana. And this way, the distribution of data among different branches of Charleston libraries are managed. So uh, okay, so what is a join? So a join can be of many types. We have inner join, outer join, left outer join, right outer join, equi joins, and then comes semi join. We will come to semi-join a bit later, but let's discuss about uh, what is primarily a join. It is an imperative operation in database theory that is used to extract information from two or more than two tables. So, join operation is one of the special cases of Cartesian product. In join, unlike Cartesian product, in Cartesian product, what do? We do not check for a condition, right? But in joins, before concatenation of tuples from one relation to another, we check for a specific condition, or a specific predicate is there in the where clause. If you consider select from where in a SQL query, then when we do select mm, start from t is select t1 dot suppose a, or the first attribute, comma t2 dot b, or the second attribute of second table, uh, from t1 inner join t2 on the uh, common attributes, where we also give another additional attribute where the joins are to be operated on those attributes. Okay, now what is a semi join? A semi join is nothing but an inner join, but a projection operation is done before the inner join part of the thing. Like we have, if we have one relation R and two attributes A B, and another relation S and two attributes B C, we can see that B is the common attribute between them. So instead of and suppose we assume that the join between R and S is going to take at the R site. we are taking the left hand side of the diagram as the R side, and instead of sending when it is it is in a distributed framework, instead of we need to send S to R to perform a join, right? So instead of sending the whole of S, we will be sending a part of S. Which part of S? Only that part which matches with the B part of R. So in this way, we will see that the transmission cost is reduced to a large extent. And what are the scenarios in which this technique is helpful? We are also going to see that. And what is a full reducer? Full reducers are like, we can have when there are three or more relations concerning to uh, join mechanism in a distributed database. uh, Joining such many relations can uh, eliminate the dangling tuples of the relations. Like if we have R, S, T, U and V, R, S, T, U and V, five relations, then if we perform a finite sequence of semijoins like R semijoin S, S semijoin T, T semijoin U, U semijoin V, like this, then we can stepwise eliminate or get rid of the dangling tuples. Or what are the dangling tuples? The redundant data, like which doesn't match. Suppose we have 10, b equal to 10 in R and b equal to 10 and 11 in S. So we only send the b equal to 10 from S to R, and we get eliminated of the 11, the b equal to 11 part. So like this, uh, all the dangling tupules get reduced in a finite sequence of joints, and we call this a full reducer. um, this can also be represented by hypergraphs. So in a hypergraph we have a year, and an edge is called a year after one reduction. So uh, as the dangling tuples or the redundant data gets reduced, the uh, the graphs, the edges of the graphs also can be eliminated. We can think of it like that. So once the graph is completely reduced, or we have only a hyperedge left with it, we can say that it's a full reducer. So now the trade-off comes between join and semi-join. So what is semi-join? As I said, if we consider R and S, and here you can see in the picture the common attribute is Y. So suppose the relation S, the Z attribute contains large values of data like audio files or video files, which are really very tedious to ship from one side to another. So instead of shipping the whole of S, can we just extract some part of S and send it to R? We do not need the other part of S, right? So only those values, only those Y values which match with R. So this is called that pi y s. This is nothing but projecting the S part of relation on the Y attribute to R, and then we perform an inner join with R. So semi-join is semi-join is nothing but an inner join, but a projection is not is a an extra step, you can say, which comes before the inner join. We have many related work to this. There are researchers who have taken up three different strategies to optimize query performance. Like they have joined two relations on a single common attribute. They have also tried strategies with more than one common attribute. Then we come to two-way semi-joins. There is a nice paper, the second paper by Numanul Subhani and Joan Morrissey, who have done good work in uh, comparing performance between two-way semi-joins and two separate semi-joins. So this is a good work. Then We have a pipeline NV join algorithm. So like the semi join is a basic, if we treat it as a basic optimization plan for a distributed query processing, and then uh, two-way semi joins, three-way semi joins, like this. Many modifications of the basic thing got evolved as per the need of the system. um, we take as our motivating example the research paper titled as Sharing Private Information Across Distributed Databases by M. Siegenthaler and K. Berman. In this paper, it is shown that data privacy is of utmost importance when data sharing comes into picture, and uh, through onion skin routing, data sharing is done from one site to another in a distributed database framework. There are three nodes or components or sites, whichever way we term them, like the data owner, the query asker, and the blind comparer. The blind comparer is a randomly generated site which is obtained by a hashing of the query asker and the data owner token. In this paper, we have an example where pharmacist needs to check if a patient might be vulnerable to a drug interaction. We will take this as a use case and implement this in our new design, an alternate design which incorporates the semi-gen operator as a reduction mechanism or a query optimization strategy to achieve better performance or to reduce transmission cost. Here, the pharmacist has a list of drugs, a table with a list of drugs that might conflict with the prescription currently being filled, and querying the system, and he wants to query the system to see if any of those drugs have been previously taken by the patient in the past. We modify this example a bit by assuming that the pharmacist has a database crash in his site, and now instead of a yes no answer from the blind comparer, now he wants to retrieve the last pickup date, as he is not able to find that from his system. So he sends out a filter query to the to a data provider. It can be a hospital or other pharmacies, and this data provider or the data owner, he should be assured that the patient has authorized a query, but they should not learn what is the data provider should also not learn what is being queried for, or from which pharmacy this query returned. So there is a large amount of data privacy, query privacy introduced in this paper, and also anonymity of communication. They have used onion skin routing, as I said, and through mechanisms like global search and data handles, they route messages from one site to another. But our main focus is in the query optimization technique. We'll also try to abide by the data privacy, the three principles that are considered in this paper: data privacy, query privacy, and anonymity of communication. And at the same time, measure the effectiveness of the query optimization technique we are proposing here. We will also see when semi-join outperforms a join, in and in which cases this alternate design should be of good benefit to the user using such a design. Now we come with our hypothesis, which is nothing but a design modification. The top picture shows the old design or the existing design of the paper we have taken in the motivating example. As we said, we there are three nodes or sites, like the data owner, query asker, and the blind comparer. In the existing design, you can see that first, the first message is sending a record access request from query asker to data owner, and at the same time, the query asker sends another request. It's not a request, but it's a query table. It's a result of cross join of two tables, and it then sends to blind comparer. So then once the data owner authorizes, sees that the query asker has enough authorization to uh, request such a record, then it sends the query result to blind comparer. So now an inner join takes place where from the table which came from query asker and the table which came and the record which came from data owner. Finally, the join result is shipped back to the query asker. But now we come with a new design where the query asker sends the filter query to the data on owner. The filter query is the query which asks for the remote data content which the query asker is not permitted to dig into directly, but this table is should not be shared also with query asker completely. So a filter query needs to be sent to data owner. Now the data owner is instructed to do two things: one, to send the complete query result to a blind comparer, and second, to send a part of the query to back to the query asker, which part only the projection of that attribute which appears in the where clause, which only that predicate which appears in the where clause of the filter query. And then the query asker sends the matches with the data which came from the data owner with the matching attribute of the joining table, that is the cross join of the local tables. And finally, it only sends those records which match to blind comparer. And then the rest of the process is similar to the previous one. So we only introduce one intermediate step where the data owner is instructed to project a part of query and send it to the query asker. In this way, we avoid shipping the whole of the cross join result to blind comparer, and only ship a part of it. We will see very soon how can this be beneficial. So now we have a use case and a sample SQL query. The use case is such that suppose there is a pharmacist who is experiencing a database crash in his site, and want a specific patient specific information from a data owner to know the last pickup date of the drug related to that patient. He sends out a filter query to the data owner and requests the record which contains the pickup date, the patient ID information, the patient information like ID, and which here we have specified as nonces. Nonces are nothing but these are the uh, patient specific information which was found in a global search. These are a combination of SSN and other patient unique identifier information. So the original query which is housed on the query asker site is that select the pickup date from we have a subquery. This is cross join between two local tables, that is conflicts and nonces, and then finally an inner join on the remote table. This remote table is the table which is housed in the data owner's site, and which the pharmacist doesn't have access to, so he needs to request the data owner uh, to let him know the particular information he wants. And you can see that the join is performed on matching attributes like nonce, like the nonces attribute of the nonces table and the nonces attribute of the drug history table. And we also have another predicate in the where clause. Uh, I, this is the constraint that the when the inner join is performed between the cross join result and the remote table, that is the drug history, the constraint is that both are to be joined based on the matching attribute, that is drug. So if you see the parse table of this SQL query, you will see that the two local tables are at leaf nodes, conflicts and nonces, and we perform a cross join and keep it on the and house it on the query asker side. And then we once we get the filter query result, or the select or the or once we extract information from the drug history table, and then we perform the final join result between these two in the blind comparer site, and this result gets returned to the pharmacist. Okay, so now suppose the data owner returns drug A to query asker. So now in the query asker has two things with him, or the pharmacist. One is a query table, that is a cross join of the local tables conflicts and nonces, and he sees that for patient ID 34 he is only vulnerable to drug A and not B. So now he only sends the first row of the table instead of sending the whole table. So in this way we avoided a part of transmission cost. This can be very beneficial if we had a large number of records in query table, and which had many attributes. Some of the attributes would have contained files like audio and video, and shipping such big records of having occupying large sizes would be really hectic. So in this way the finally the join is performed between the query table and the record which is sent from data owner to blind comparer, and we only retrieve the pickup date and sent it back to the query asker. So we now come to performance of the system. Uh, the first case is that suppose for a particular patient ID, the data owner doesn't return any record. So now we know that the blind comparer also doesn't have any record for a particular patient ID, and and it there is no need to send the query table also as like there will we know that there will be no inner join result be returned from the blind comparer. So if we had this step of returning a part of the filter query result back to the query asker, we can save the overhead of sending the query table from the query asker to blind comparer. Also, as we have said that the local tables at the leaf nodes, if they have large number of attributes, and the components of the attributes, if they are files like audio, video, or documents, then sending such sending such tables having such big records would be really very tedious. So we need to compute two things. One is the S cost, or the cost of performing semi join, and the J cost, the cost of performing the natural join, that is the join between two tables, by either shipping T1 from site 1 to site 2, or shipping T2 from site 2 to site 1, wherever the join operation is going to take place. If S cost is less than J cost, then semi-join is useful, otherwise we should go for join. So we concluding our work that by saying that semi-joins are helpful in optimizing the join query by reducing the quantity of data exchange. We have seen that we can extract a part of the table records, and instead of sending the whole of the relation, we can project a part of it and send only which are needed or which match with the joining attribute of the joining table. So when data transmission cost is of main consideration, we should think of such optimization plans. It definitely increases local processing cost and the number of messages interchanged between nodes, but at the same time, data transmission uh, can be reduced. And like if we have the links between sites, as in a weak state, like if a phone or wireless link is of low capacity, then we need to think about such query optimization plans, so that transmission cost can be reduced. We will think of improving performance of joints over this, over the semi-join operator we have, which we have talked about in this design. We can think of perf joins, Bloom filters, two-way semi-joins, a combination of join and semi-join, different various ways or techniques to improve the join performance between relations in a distributed framework. All for today. Thank you.